Today I'm bringing another statics video, and this one is on frames, the topic of frames and machines. And this is typically a topic you see towards the end of the semester, but I wanted to show you this problem because there are a few things that you need to be aware of when you're approaching a frame or a machine problem. Okay, and I do want to share some of the tips that I, carry with me when I go solve these problems. Okay, now this one in particular, as you see, there's some parts that are kind of weird. Um, there'll be parts where a lot of information is going on, but I'll walk you through it, and then let's see if we can do this. Okay, so first things first, read the question carefully. So it says a wall crane supports a load of 700 pounds. Find the vertical. So find vertical horizontal components for the reaction at pins A and D. So find AX, AY, DX, DY, and what is the cable tension at the winch W? So find T, right? Member ABC weighs 100 pounds and the member BD weighs 40 pounds. Assume that the members are uniform and that the center of mass is at its center. Okay, so first things first, right? This problem is a little bit funky because um, there's a lot of different pulleys and a lot of different things, but on top of that, they decided to give us the weight of a couple members, right? That's not very usual, right? Not very usual. So that changes the analysis a little bit, but not too much. So the weights are going to be applied as if they were external forces, which kind of changes how we would interpret member BD. If it wasn't for the weight, I would certainly say this is a two-force member, therefore a lot of the unknowns, two of the unknowns would become one, and that would make our life easier. I'm not sure too much about with the weight there. I would keep it this way and just analyze it that way. But the first thing that I want to do is just solve for general equilibrium, right? So that's the first thing that you usually want to at least attempt. And if you can't solve for anything, just keep the equations for reference. They'll help you at least double check your answer in the end, if anything. But a lot of times they'll help you solve for an unknown or two at the end. All right, so general equilibrium. Sum of the forces in the x, we've got positive 2 to the right equals to 0. AX, we also have dx, the way we define them up to us, right? We have negative t cosine 60, and just explaining that t is going this way, it has a component going down and one going to the left. This is the one that we're worried about is going to the left, so we define positive to the right, so minus t. The angle is 60 and it's an adjacent vector to the angle. So cosine 60 equals 0. All right, we can't solve anything there, right? And that's it for that. Sum of the forces in the y equals 0, positive up. Let's see if we can pick up anything, right? We've got AY plus DY minus 40 minus 100 and then minus 700. All right, can't do anything. Two unknowns, one equation. Let's save these two equations, right? And then typically you could do a sum of the moments about a certain point there for the general equilibrium. I'm not going to do it because there's a lot of information missing, and that includes the size of the two pulleys that are involved, like the two bigger ones, B and C, and that does affect, our ability to take moments because we wouldn't have the correct distance. And so I'm skipping the moment, okay? But usually you could do a moment and also try to get more equations. One more equation and some unknowns out of it if you want, okay? In this case, does not apply. Okay, so let's just skip to analyzing one of the members, and now obviously let's keep these formulas there. So I'm going to choose to analyze member A, B, C first, okay, because it's the biggest member. There's a lot of information there that we could possibly get. So here, the first thing that you want to do is at A, we're going to draw AX and AY exactly like we did in our general equilibrium, exactly like you did in our general equilibrium free body diagram. Why? Because we're still analyzing that exact same pin that involves the exact same member. If If we're analyzing another member, or let's just say the wall in that case, then the directions will change. But in this case, exact same direction. Okay, very important, very important. We got B here, and in B, there's a lot of stuff going on. Okay, there's a lot of stuff going on. There's a pulley that's attached there. There's the reactions of the pins there. There's also a lot of influence from member BD. But what I'm gonna do is I'm gonna keep it simple, because I'll just say, like, hypothetically, everything is part of BX and BY. Okay, but we're not gonna solve for them. We're gonna completely ignore them, and we're gonna solve it a clever way to try to avoid all the trouble that that little region has. Okay. And I'm doing that as a strategy because it just makes it so much easier. And quite honestly with you, there's so much going on there that I'm not really sure how to approach it in a solid and correct way. Okay, but there is a way. I just am not very familiar with, and I do know that there's a way to bypass it. Okay, and then what else do we got? So remember, BX and BY is including everything that's going on at the pin and also the tension. We're not going to solve for them. And then we do have some stuff here at C. So what I'm going to do is I'm going to draw CX this way, and then CY going down. Okay. And I would know stuff about C though, because there's a pulley there, and in that pulley there's a system that allows me to solve some information about CX and CY. So how about we take a small detour and we solve for the pulley on the side. I'm going to be on the upper right corner. Okay. So solving for CX and CY at the pulley. Okay. This we can do. This pulley we can do and should do. So first things first, that bottom pulley, okay, it has that 700 force pulling us down, right? Which means that these two have to be 350 to balance it out, okay? By the way, we don't have friction on those pulleys, so it's 350 across the cable, right? Which means that Newton's third law says that the same thing would apply at the, oh, I should have drawn it at the center, but the same thing would apply at the other parts of the cable, okay? So Newton's third law allows us to make that claim, okay? And because it doesn't have any friction, then these would be, the bottom ones would be equal and opposite. And then the one going up top, it's because it's the same cable, right? It's the same cable wrapping around with no friction. It's the same value, right? And then obviously the same reactions CX and CY that we were interested in the first place, right? So, but this time around, different bodies, so we have to draw them equal and opposite, right? So we drew CX going to the left, we have to draw it going to the right, and CY we drew it down, we have to draw it going up, okay? So now that we did this part, the bottom part, I'm going to ignore it, okay? This was just like a middle step of our detour, right? Remember we were doing a little bit of a detour? We're going to ignore this, okay? We're going to ignore this. There's no need for it anymore. It was already transferred over. It's not going to be a need anymore. So sum of the forces in the X for this system here, right? And put like an arrow, bigger arrow, so it doesn't confuse us, equals 0. Positive to the right, okay? Cx is equals to 350, right? It's the only force present there going in the X direction. So we got that information, okay? Now sum of the forces in the Y equals 0, positive up, tells us that Cy is equals to the sum of the other one going down, which is 700. Boom. We got some valuable information about this system here. So this was 350, okay? And then this was 700, okay? So now that we got that, what we're going to do is we're going to be smart about all the stuff that's happening here at B, and we're going to take a moment about B, okay? And the reason for that is because that will allow us to just completely ignore everything that's going on there, because BX and BY and all the stuff that's involved with it, would not cause a moment. So the only two things that would cause a moment is CY and AY. Okay, CY wants to rotate this clockwise, and AY also wants to rotate this. If we pin it at, let's just say we fix point B. Okay, AY would want to rotate us clockwise, and so does CY, and we defined counterclockwise positive. So both would be negative for starters, right? So minus AY times distance of 4, that's the distance we're away to B, and then minus 700, also 4, that's equal to 0, which means that AY is equals to negative 700 pounds. Boom. One unknown done. One major unknown done, which is part of the question. So this one is done, right? And then we're set with this member, okay? Remember, I mentioned that I didn't want to involve bx or by, so we can't really do some of the forces in the x or some of the forces in the y. We're just going to try to avoid it. And you see that when I analyze the other member, which will be member, really I should have drawn it the other way around, but it doesn't really matter. I kind of wanted to have this like on top of ABC, but that's fine. Member BD. Okay, so we have a weight here, which was 40. And we also have to be consistent here and mimic what we had in the overall free body diagram. Same exact thing, doesn't change directions. This one, though, would change directions. But remember, we're not going to use them, right? We're going to try to avoid them like the plague. We're going to avoid them like the plague. So the idea here is that we're also going to take a moment about B for convenience. Okay? And that is equal to 0. Okay? So dx and dy, okay, would be the only things causing a moment. All right, let's see. So dy, if we pin ourselves at B, okay, if we hold B steady, would want to rotate us going clockwise. So minus dy times that distance of what? 4. And then dx would want to, if we translate that force here, it would want to rotate us going clockwise as well, right? So clockwise. So minus dx times a distance of also 4, right? And then 40, if we translate that force down, okay, we got 40 wanting to rotate us this way, counterclockwise, right? So plus 40 times the distance of 2, because the weight is right in the middle as the problem stated, right? Equals 0. We have two unknowns, right? We have two unknowns. Only one equation because we're avoiding some of the forces in the x and some of the forces in the y due to everything that's going on in at B, right? But the thing is that we ended up picking another unknown that the problem wanted without really realizing that we did, and that was, which I'm going to highlight for us, that was tension. Okay, when we did this little analysis here at the right corner, when we found CX and CY, we ended up actually figuring out what tension was. Tension is literally what's going on through here, right? Same cable, right? So the tension really is 350 throughout the cable. No matter where you are at that cable, it's 350. So T is equals to 350. And then if we go back here on this equation here, we can solve for AX, right? Or I should say, we could solve. Let me think about it. Am I making a claim that's going to allow us to figure this out? Hold on a second. Might be missing something because let me think about it real quick. Did we figure out what oh, okay. Yeah, we're not, I mean, still a valid claim, but really it won't really help us, okay? You see. Let me just make that substitution already, just because I already mentioned it. But it's not really going to help us, at least for now. That's okay. That's okay. We'll manage. It's the other equation that will help us. Okay, it's the other. Why? Because we already figured this bad boy out. So this one will be minus 700. So if I do it this way like that, okay, the two equations, plus dy. So we'll be able to get dy out of this one, okay, plus dy minus 840, which I think was, right? Oh, I missed that's why I was, because I already like kind of solved the problem in my head before I even like started the video. So I'm missing here, guys. I'm missing tension going down. So minus t, that's why we need tension. Minus t sine of 60. There we go, equals 0. Okay, that's what it was missing. Big mistake, but not anymore. So t was, let me cross it out, t was 350. Boom, we can solve for dy. So dy turns out to be what? With all this going on, we have minus 840 minus 350 times sine 60, then minus 700. Let me just see something. Did I do this correctly? Minus 700 minus 840. Just double checking my work here, guys. Give me a second. 700, 840. That should be right. That should be right. Okay, so this turned out to be 1843 pounds. Pretty big number. Okay. The reason why I'm questioning it is because I wanted to see, yeah, that should be right. Because, yeah, AY is negative. So that's going to add up to all those values that we had before. Minus 800, 840, and then that with the sign. Okay, that makes sense. All right, so dy was this. Boom. Okay. dy was that value. Then we can take this and plug it in there and solve for dx. There we go. There we go. So minus 1843 times 4 minus dx times 4 plus 80 equals to 0. Dx is equals to, so dx is equals to, so times 4 plus 80, 4, 1823. There we go, 1823. Good stuff. I think this is all correct, guys. And then this was supposed to be negative, by the way. Or no? Let me think about it. When I move it to the other side, this becomes positive. Yeah, this was supposed to be negative. There we go. Okay, so dx is this value. Okay, and all right, so we have dy, we have dx. We also have, let me just check these. dy, dx, t, and we're only missing ax. So let's step here. Ax minus 1823, right, from dx, minus 350 cosine 60 is equal to 0. Boom. Ax is equals to what? So minus 1823 minus 350 times cosine 60, we get a positive answer of 1998. This is also in pounds. And I think this is it, guys. I mean, we did everything the problem was asking, okay? And we did it very clever, in a very clever way. Because let me tell you something. When I looked at this problem at first, right, when I was like trying to brainstorm before even starting this video, I realized that there were way too many connections going on here, okay, at B. Way too much stuff. Okay, so after I realized that, I was like, I need to figure out a way where I could still solve this without having to deal with all that stuff that was going on there, okay? So by being clever about it, I was able to work around it. And a lot of times on these problems, you have to do that, okay? And that's why I think this problem is so cool, because not only does it take the understanding of frames and machines, it also ended up including weight, which changed our analysis a little bit. And it also involved pulleys. So a lot of good stuff going on. So the takeaway is, okay, takeaway, and I'm going to use my highlighter to help us visualize what I'm talking about. First things first, in yellow, general equilibrium, right? Draw your beautiful free body diagram, do that general equilibrium from there. Try to include the moment if you can, if you have enough information. I couldn't in this case. If you can't solve for stuff, leave it as an unknown, leave it as an equation. You might use it later. Second takeaway, take apart the members, okay? So everywhere you see a pin, there should be at least two reactions there, okay? So for instance, at C, I got CX and CY, okay? And then it turned out that it's the same reactions. I mean, not that it turned out, but it's supposed to be that it's the same reactions where it's attached to, like another member that it's attached to, just equal and opposite. So at the top right corner, equal and opposite at the pulley, okay? So where you take that pin apart, you do that. Same thing applied at B, okay? It just happened that I didn't really look into the information there. So I don't know how much of BX and BY involves the tension. I didn't really include the tension, to be honest, because I think it's embedded in that information, but it could be like a wrong interpretation. What matters though is that I did, solve it in an elegant way, which makes the solution still extremely valid and correct. Okay, so besides flipping these, it's important to keep track of them, right? Keep track of them. So try to do your free body diagrams very close to each other, so you can make sure that you're really drawing them equal and opposite, right? And then besides that, guys, it's just every member that you take apart, you get three equations to work with. Two sum of the forces, x and y, obviously, and one moment equation. So every time you take a rigid body apart, obviously with the exception of a pulley or a two-force member or something like that, you have three equations to work with. So very good stuff. You can solve for tons and tons of unknowns. For instance, if I had worked out what was going on at B, okay, included that tension and all that good stuff, I could definitely figure out what BX and BY really is, okay? But I'm assuming in this analysis that BX and BY already includes the tension, okay? All right, so this is it. That's it for it today, guys, for this video at least. Please let me know if you like this. Also, let me know what you would like to see. And I really hope that this helped some of you that may be trying to learn this. I remember when I was learning, it was very confusing. So I just want to help you guys out. Take care, guys, and I'll see you in the next one. Take care. Thank you.